Let's see, 0.156 gram sample of magnesium aluminum alloy. Dissolves completely in excess HCl. What a lot of people do on this particular problem is they assume it's a one-to-one. So it's aluminum and magnesium alloy. And so they do aluminum plus magnesium plus HCl. And then they come up with a balanced chemical equation for this. So it's going to form aluminum chloride and magnesium chloride and hydrogen gas. And then when they balance this, they'll get the aluminum, magnesium, and HCl coefficients. But what's the problem with this?
You have to do it individual.
Yeah, you have to do it individually. You can't combine these into one equation because what that does is it fixes the ratio. And it's a mixture, so we can have these in any ratio we want. So do this. We have to do it individually. So we'll have aluminum plus HCl. This is going to yield aluminum chloride. HCl is just a mineral acid, so this should work using the single replacement reaction. And now we can balance this. So we'll need 3 HCl, and we're going to generate 3 halves of hydrogen. We can double it to get rid of the fraction. And the magnesium requires 2 HCl. And so we get different amounts of hydrogen. And so this allows us to tell how much each is present depending on how much hydrogen we get. And so aluminum and magnesium have roughly the same molar mass. And so it looks like aluminum produces more hydrogen per gram than magnesium does. The reason this is an advanced problem is because liberated hydrogen is collected over water at 5 degrees C, and the barometric pressure is 752 torr. And so whenever we collect a gas over water, the water is going to contaminate the gas. So, excuse me, if the water is in contact with the gas, then some of the water is going to vaporize. How much water vaporizes depends on the temperature. Now, there are 2 ways of handling how much water is in here. Water vapor, that is. This is water liquid. And then we have water vapor. The 2 ways of handling this is, one, well, actually, we can figure out of this volume how much is water vapor. And so what is the volume of the gas that they collected? 202 milliliters. So they collected 202 milliliters of gas. So out of that 202 milliliters, how much is water? That would be an example of what? Well, most of this gas is going to be hydrogen. So we have hydrogen. Most of the gas is hydrogen, but we're going to have a little bit of water. And so how many of these milliliters is hydrogen? How many of these milliliters of water? That would be an example of Dalton's or Avogadro's mixture.
Dalton's, right?
And this is what we say in Dalton's. In Dalton's, how much hydrogen was collected? Pure hydrogen. how many milliliters of pure hydrogen were collected using Dalton's?
202 million.
202 milliliters. And how many milliliters of gaseous water were collected using Dalton's? 202 milliliters. And so if we use Dalton's, we have 202 milliliters of hydrogen and 202 milliliters of water. So what must be the difference? The difference must be the pressure that they generate. That's right. And so if we do this via Dalton's, we can figure out the pressure of water. The pressure of water is this. What's going to happen is the water is going to vaporize, and then it's going to reach a state of dynamic equilibrium. In the state of dynamic equilibrium, the rate of vaporization here is equal to the rate of condensation there. And so what we end up with is a steady amount of water vapor. And that steady amount of water vapor is going to, again, depend on the temperature. The higher the temperature, the more water we get, the more humid it is. The lower the temperature, the less humid it is. And so the temperature for this is 5 degrees C. At 5 degrees C, we're going to generate a humidity. Now, the humidity is going to depend on how many water vapor molecules are in a given volume. The bigger the volume, the more water vapor. The smaller the volume, the less. In other words, the concentration is going to be the same. The concentration is the same, but that means the pressure is going to be the same. So we look up the vapor pressure of water that's fixed at 5 degrees C. And they didn't give it to us in this problem. We don't have to have that memorized. They must have given it to us in the note. Oh, they did give it to us in this problem. The vapor pressure of water at 5 degrees C is 6.54 millimeters of mercury. And so the pressure of the water vapor is going to be along 6.54 millimeters of Hg. So normally when we measure this gas sample, we measure the entire pressure. We don't measure this we get out of a book because that's how much water it will take to saturate it. So we're going to generate the pressure of that. If we have a bigger container, more water will evaporate, but we'll still have the same pressure. So what they did was they equalized this with barometric pressure. And so the pressure of the mixture is equal to the barometric pressure, which is 752 torr. Dalton's law says this, that's going to equal the barometric pressure, which equals the pressure of the wet hydrogen, which equals the pressure of the dry hydrogen, plus the pressure of the water vapor. The pressure of the water vapor is 6.54 torr. You want to use the same units, or 6.54 millimeters of mercury. A lot of people prefer using torr because it's less characters. It's 1, 2, space 3, 4, 5. This is 4. And so we don't know what the pressure of the dry hydrogen is, so let's go ahead and figure out. The pressure of the dry hydrogen is going to be 6.54 torr. And so, solving this equation, the pressure of the dry hydrogen is equal to 752 minus 6.54, which is going to give us 745.8 0.546 torr. We're only allowed, actually allowed no decimal places, so 745 torr, but I'm not going to round it yet. We'll round it later. We end up with 3 sig-figs. So the hydrogen is going to generate 745 torrs worth of collisions, and the water is going to generate 6.54 torrs worth of collisions, and altogether it's going to add up to 752 torrs worth of collision. So this is what you do when you know this stuff pretty well, you know, Avogadros and Daltons. Then you think, okay, how could I express this? Remember we did it with air in some other stuff. We did Daltons and we did Avogadros. How could I express this in terms of Avogadros? In terms of Avogadros, we think of it differently. So when we think about Dalton is constant volume. All the gases have the same volume. So everything's going to have 202 milliliters. The difference is the pressure. So the volumes are all the same, but the pressures are additive. This will be an aside. This is what I did. You know, this is why what I did for homework too. You know, because I used to review my notes and then I review the homework. But when I did the homework, I always thought about additional twists on the homework. So, for example, this problem, okay, we'll just leave that. But then I might start thinking about something like this. How would I, you know, this would be a side topic. How would I have visualized this as an Avogadros mixture?
Pressures are constant.
Yeah, the pressures are constant. And so I would have, how much hydrogen? I'd have 752 torrs worth of hydrogen. And how much water vapor? I'd have 752 torrs worth of water vapor. So what's the difference? The difference in volume. So out of that 202 milliliters, how many milliliters of hydrogen and how many milliliters of water vapor do I have? Could you figure that out? All right, how would you figure it out?
Mixture equals volume of the H2 plus the volume of the H2O.
Yeah, the volume of the, we'll just say the mixture or the wet hydrogen. The volume of the mixture is equal to the volume of the wet hydrogen, which is going to equal the volume of dry hydrogen plus the volume of the water vapor. Okay, now the question is, what is the volume of the dry hydrogen and what is the volume of the water vapor? So out of this 202 milliliters, how many of this is dry hydrogen and how many of it is water vapor? Or pure hydrogen, pure water vapor?
Oh, wait, no, that's not a direct conversion, right? What do we have to do the ideal gas law?
Actually, we don't, we could, I guess we could do the ideal gas law, you know, because we have all the information here to figure out how many moles of hydrogen we have. Did they give us the temperature? Yeah, 5 degrees C. So we could use the ideal gas law. There's another way of doing it. The other way of doing it is knowing this. Do you guys recall this? The mole fraction is equal to the volume fraction, which is equal to the pressure fraction. And so I think that one of the quickest ways of doing this is this. If I look at the wet hydrogen, this would probably be the quickest way. The wet hydrogen hydrogen has a pressure fraction of what? Okay, the hydrogen has a pressure fraction of 745.46 out of a total of 752. So this is the pressure fraction, and then the volume fraction is going to be the same. So I'll just times it by the total volume, 202 milliliters. And so that's going to tell me how many milliliters of dry hydrogen I have. And so the volume of the dry hydrogen would be 745.46 divided by 752 times 202. This gives us 200.2 milliliters of dry hydrogen. Plus, what volume of water vapor do we have? Well, what's the pressure fraction of water vapor? It's going to be 6.54 out of a total of 752 torr times the total volume of 202 milliliters. So this would be the volume fraction for this. 6.54 divided by 752 times 202, 1.75. 6 milliliters of water vapor. So in terms of Avogadro's, we take 200 milliliters of dry hydrogen and 202. It's going to add up to 100 or close to it. This is round off error. This is going to be round off error. It's going to come out to 201.956, but this I should have carried more digits. There's a problem with rounding. Things don't add up sometimes. But 200 plus about 2 gives us 202 milliliters. Does that make sense? Mm-hmm. So sometimes you do this. Sometimes you do this to think about, different ways of visualizing these things. So.
Still, we couldn't, in this particular problem, we couldn't do Avogadro's without doing Dalton's first to get the pressure of the water vapor.
Yeah, exactly right. If we go to the vapor pressure table, we would have to do this because we need to do Dalton's because the volume fraction is what we call extensive. It's going to depend on how big this container is. And so volume fraction is extensive, whereas the pressure fraction is intensive. And so this is why water vapor pressures aren't listing how many milliliters of water vapor you have, because that would be depending on how big the container is. But interestingly, the pressure fraction is, if you increase the size, we're going to have more vaporization. And then eventually equilibrium will be reestablished, but the new equilibrium will have the same gaseous concentration as before. Or you shrink down the size, we'll have more condensation. And so the pressure here is going to be intensive, the vapor pressure of water. And this is why the vapor pressure of water is such a useful thing, and this is why we can just read it right off the table. However, the pressure fraction can depend on how much you had. And so if we had 760 millimeters of pressure that day, then the pressure fraction would be different, which would give us a different volume fraction. And so we did have to do the pressure fraction first. So those are the types of things that you notice when you go through problems over and over. You might think, okay, I just did this problem once, but sometimes, you do it multiple times. which I found, sometimes I found that more useful than rereading the chapter. I never really read the whole chapter in depth, just the stuff that was covered in class. All right, now that we have this, what are they asking for? Well, obviously, this is an advanced problem. So it being an advanced problem, they're going to add an extra step here, or two. And so after the gas is collected, the water and gas gradually warm to the prevailing room temperature of 23 degrees C. Now, this is a bit difficult here, because did it warm? When they say the gas warm, did the liquid warm too? Is the liquid still in contact with the gas? If they stop it here and then remove the gas so that no more liquid can evaporate, then we have a fixed amount in this container, fixed amount of water vapor. However, and this is not entirely clear here, and gas gradually warmed to the prevailing room temperature of 23 degrees C. Okay, it is clear here, because you see they said the water in the gas. So if the water and the gas warm up here, then as the water gets hotter, it's going to make the air more humid, or the gas more humid. It's not air, but the gas more humid. It's going to change the pressure fraction, and it's going to change the volume fraction of water vapor in there. The pressure of the collected gas is again equalized against the barometric pressure of 752 torr, and its volume is found to be 202 milliliters. Okay, then I made a mistake, because this volume, they didn't give us the volume at 5 degrees C. If we warm the gas up from 5 degrees C to 23 degrees C, then the volume is going to expand if the pressure stays the same, and it looks like the pressure stayed the same, 752 and 752. And so this is the final volume after this. So I might have just wasted a lot of time doing that. This is another reason you should read the whole problem before doing it. Because I should have read the whole problem before doing this, because did I have to even worry about the 5 degrees C? No, I didn't have to worry about the 5 degrees C. That was extra information to throw you off and waste your time. And so I was thinking, that happens. Sometimes they'll throw in extra information, and sometimes you feel like you're obligated to have to use all the information that's given. And so this was an advanced problem, because I didn't need to do that. Instead, okay, the gas warms up, and so what's the final state condition of the gas? So the final condition of the gas is now we have 202 milliliters of wet hydrogen. Okay, we can't do Avogadros with vapor pressure. The vapor pressure of water, this is at 23 degrees C. And we still have the water in contact. And so there's going to be liquid water here, and then there's going to be water vapor here. And then we have our hydrogen in here. Okay, so what we want to do is this. We want to know how much dry hydrogen we have. And so, because we'd like to calculate the moles of hydrogen. Which we can. But then we're going to have two unknowns and one equation. And so what we're going to do is I'm going to use the method that we did for solving some of these other two unknown problems. And that is this. We're going to have 0.156 grams of mixture. This is going to be magnesium and magnesium and aluminum. And we don't know how much magnesium and how much aluminum there is in this mixture. So this is what we're going to do. One, we can go all the way to, well, actually, there are a bunch of ways we can do this. Probably to keep it simple, I think what we'll do is we'll just take it all the way to wet hydrogen. All right, so one, we'll assume that the mixture is 100% magnesium. If the mixture is 100% magnesium, then I'm going to have 0.156 grams of magnesium. And then we'll just convert that into moles of magnesium, which would be 24.31. And around this, 24.31 grams per mole. And then we're going to go to hydrogen. 1 mole of hydrogen for every 1 mole of magnesium. That's from the balanced chemical equation. Okay, once we have the moles of hydrogen, then what can we do?
We can assume 100% aluminum. So,
Well, we can go from moles of hydrogen to volume of hydrogen, right? Or we can go from moles of hydrogen to pressure of hydrogen. Which one should we do? Should we go to volume? All right. If we go to volume, what I'm going to do is I'm going to calculate the molar volume. What was the molar volume again? It was V over N, which is equal to RT over P. And so R is going to be 0.08206 liters atmosphere per mole Kelvin. T is going to be 273 plus 23 is 273 plus 23 is 296 Kelvin. P. Should we do about P?
We're going to assume that it's all H2. So, we'll just use that.
Subtract 21.07 from 752 and then convert it to atmospheres.
Okay. So you're going to take 752 minus 21.07, which is the vapor pressure, and convert it to atmospheres, and that would be the pressure of that. Okay, so you're saying that the pressure of the dry hydrogen is equal to the pressure of the wet hydrogen minus the pressure of the water vapor. And so the pressure of the wet hydrogen is 752 for minus 21.07 for, which is going to give us 730.93. of dry hydrogen? Yeah?
One thing though,
Mm-hmm.
you know how, like, this section we were talking about how you use the constant to create the graphical method, right?
Mm-hmm.
I did it using this method and I got the wrong answer.
For this problem?
Yeah.
Okay.
And so instead of going from grams to volume,
Mm-hmm.
I went at the very beginning, I just got moles of H2 from the grams,
Mm-hmm.
and then I used that to go to grams of magnesium and aluminum to create do the graphical method. Because isn't this, like, we're getting
The moles of H2 is going to depend on if you're doing magnesium or aluminum. And so, how did you get the moles of H2? Which one did you choose for that?
I went from grams of sample.
The grams of sample is going to be magnesium and or aluminum. And so, how did you do that? I mean, you have to, what did you do? I mean, for this, how did you go from grams to moles?
Yeah, well, that's what I did at first, and then it was the wrong answer. But for this one, to get moles of H2, I used ideal gas law.
Okay.
Using the, oh, sorry, I didn't use the grams. I used 202 milliliters.
Okay.
And then from there, from moles of hydrogen, I got grams of magnesium and grams of aluminum. And I used that with the graph.
Okay.
Yeah. It's weird. It could be like changing depending on the.
Yeah, so what you did was you worked backwards from 202, but 202 is kind of in the middle again, so it's kind of the,
So this is one.
yeah, it's going to be, the problem is it's not going to be at the limit.
So that's what they did on the answer key.
Did they do that on the answer key?
Yeah.
That's odd. Well, let's see how I mean, there are multiple ways we could do this. But if we do volume here, then, and we calculate the volume of the dry hydrogen, could we calculate the volume of the wet hydrogen from that? We could. So we have two choices here. From moles, we could go to volume, or from moles, we could go to pressure, because this is moles of gas. Temperature's fixed. And so if we go here, moles, we go to volume. Is that what we want to do? Okay, if we go to volume, let's go ahead and calculate this. Now the pressure we're going to use is which one? And so this gets complicated because now we have to think, you know, are we going to fix ourselves in Avogadros? Or are we going to fix ourselves in Daltons? Because we can't switch back and forth until we complete it. And so here we have to commit. Are we going to go for Avogadros or are we going to go for Daltons? Because that's going to dictate how we decide what the pressure is. If we go for Avogadros, then the pressure of dry hydrogen is not this. If we go for Avogadros, the pressure of dry hydrogen is 752. See, I'm going to make a big mistake here if I do volume here, because I already said I'm going to do this based on Daltons. If I do Daltons, I already know what the volume is. What is the volume? 202 milliliters. So right now we have to decide what we're going to do. Are we going to do this as a Daltons or are we going to do this as an Avogadros mixture? And that's going to dictate how we handle pressure and volume because we'll handle it differently in this particular problem. Does that make sense? And so this is what it looks like. It looks like this. If I go ahead and did this, like was mentioned, well, if we want the pressure of dry hydrogen, take the total minus the water. That gives you the pressure of the dry hydrogen. Then I fixed myself. I should look at this strictly as a Dalton's, right? Because Dalton's, we add up the pressures. And therefore, if I fix myself to Dalton's, then here I do not want to calculate volume because I already know what the volume is. Here I want to calculate the pressure. And so what I'm going to do here is I'm going to stop here. I'm going to stop and get the moles of hydrogen. This is going to be dry hydrogen. And then I'm going to use the ideal gas law. The pressure of the dry hydrogen is equal to the moles of dry hydrogen times R times T divided by the pressure of dry hydrogen. That will give it to me. And so here is the pressure of dry hydrogen I have in the final mixture. You know, this is what we got from the experiment. Okay, and so let's go ahead and figure this out here. So I'm going to go ahead and calculate how many moles of hydrogen I have. And so I'm assuming it's 0.156 grams of pure magnesium divided by 24.31, and that's going to give me 0.00641 moles of dry hydrogen. Then I'm going to plug it in here, times R, 0.08206, times T, 296, divided by P. What is the pressure of the dry hydrogen? Not the pressure, sorry. What is the volume of the dry hydrogen? I'm sorry, the volume. The volume of dry hydrogen. What is the volume of dry hydrogen? It's 202. It's 202 milliliters. Because this is a Dalton's. And so this would be 0.202 liters. And so I'll divide it by 0.202. And I get the pressure of hydrogen that I generate, dry hydrogen that I generate is 0.7716 atmospheres. And then I'm going to divide this by 760 torr per atmosphere. And I come out to, I better double check my numbers, 0.0001015 torr. Seems awfully small. That's barely any pressure at all. I must have made a calculation error. Let me just check it, double check my calculations here. 0.156 divided by 24.31 times N, or 0.08206 times T, 296 divided by B, 0.202. Yeah. 7716 atmospheres divided by times 760. Not divided by, I made my mistake there, times 760. 760 torr per atmosphere. This is awfully small. So 586.4 torr. So could this be pure magnesium? No, it can't be pure magnesium. And so the next step is we're going to assume 100% aluminum. And so 0.156 grams of aluminum, or mole of aluminum, weighs 26.8 And then it was a 3 to 2 mole ratio, 3 moles of hydrogen for every 2 moles of aluminum. And then I'm going to stop here. And I'm going to calculate how many moles of aluminum. So 0.156 divided by 26.98.
Well, I got a 6 to 2, like 3 to 1 ratio. Is that right?
Oh, 6 to 2? Yeah, multiply, what did I get? Okay. Aluminum plus HCl yields AlCl3 plus H2. So I got 3 here, right? Which gives me 3 halves here. And then I just doubled it. And so I got 2 aluminums plus 6 HCl yield 2 AlCl3s plus 3 H2s. That gives me 6 hydrogen, 6 hydrogen. So I have a 3 to 2 ratio. Can you check yours? Well, let me check this. Let me, did somebody else get that?
Yeah, mine's wrong.
Okay. So we have moles of dry hydrogen here. Okay, now we're going to calculate the pressure of the dry hydrogen that we would have gotten from this. And so it's going to be this times R, 0.08206, times T, 296, divided by V. Now, that's going to again be 0.202, which is going to give us 1.0429 atmospheres times 760, which is equal to 792.6 torr. So could this be pure aluminum? No, so it's in between. And in fact, it looks closer to aluminum than it does to magnesium, doesn't it? And so there's got to be more aluminum in this than magnesium. Like I said, I could have solved this problem using, in fact, I was going to solve this problem using Avogadro's. My first choice would have been to do Avogadro's. With Avogadro's, I would have gotten volume of dry hydrogen, and that way I wouldn't have to stop here and do this. If I would have gotten volume with dry hydrogen, then I would have used this, and then I would have just had one conversion factor rather than stopping and then using the ideal gas law. And so my first original thinking on this was to use Avogadro's. But it's fine. You could do it either way. You could use Avogadro's or you could use Dalton's. And so if we use Dalton's, we don't need the molar volume. I would have just tacked on the molar volume here and calculated the volume of dry hydrogen, and then I would have figured out how much volume of dry hydrogen is in here using Avogadro's. Okay. The problem with this particular question is that people get it mixed up. They start mixing up Avogadro's and Dalton's and start using the wrong volume and the wrong pressure for their calculation. And it screws things up. But anyway, here, if we had 100% aluminum is going to give us more. Then we're going to have 792.6 torr. worth of hydrogen gas. If we had 0% aluminum, that is 100% magnesium. If we had 100% magnesium, 0% aluminum, we're going to get 586.4 torr worth of pressure. This is the pressure of hydrogen dry. And so we have this linear relationship. So Y is equal to mx plus b. Y is the pressure of dry hydrogen. M is the slope. So 792 minus 586.4. So 792.6 minus 586.4 equals 206.2 divided by 100. It's 2.06. So the slope is 2.062, and the units will be torr per percent aluminum times X, which is percent aluminum, plus B, which is 586.4 torr. So we are given Y here. And the Y is 730.93 torr. 730.93. So this is equal to 730.93 torr. So we'll take 730.93 minus 586.4 divided by 2.062. And so X is equal to 70.09%. It looks like we're probably equal 3 sig fig, so we'll just go with 70.1% aluminum. And that would make it 29.9% magnesium. I mean, we were already expecting more aluminum than magnesium. But what did the book get? I'm curious what the book got. 69.7% aluminum. All right. And I guess it's close, so it could be due to rounding errors, maybe. I don't know. The book has a habit of rounding a lot more than what you should, and so after each step, or I could have made a mistake with my rounding. I rounded magnesium's molar mass. The book might have carried more digits. So as long as you're close like that, it's okay. Do you want me to solve this using Avogadro's or no? All right, let's not. You're probably tired of Avogadro's and Dalton's.
I'm just
Well,
tired of this specific problem.
Tired of this specific problem? Yeah. Yeah, this is this is the last of the Chem problems, so this is probably the most difficult problem in the chapter, maybe. Okay, other questions? We'll move on from this one. Uh-huh. Uh-huh. Thank you. What problem?
So I'm going to start with number 17. I was saying it's going to be false, but I was confused about the pressure and all that.
17 is not false. It's true. We have 1 liter of air. What's always true is the mole fraction or the mole percent. Let's say it's 80% nitrogen. This is always true. It's 80 out of 100. This is what we call the mole fraction. That's always true. And so let me just boil it down to this. If we call this Dalton's, then 80% of the pressure is nitrogen. If we call this Avogadro's, then 80% of the volume is nitrogen. But it can't be both together. And so in this case, the pressure, 1 atmosphere versus 0.8, that's 80% of the pressure. So the situation here is, if 80% of the pressure in this container is nitrogen, then we can't do anything with the volume. And so 1 liter of air at 1 atmosphere is going to have 0.8 atmosphere of nitrogen. But can we say it's 0.8 atmospheres of nitrogen and that is 80% of the pressure and 80% of the volume? And so in other words, can we take 80% of this is nitrogen, therefore 80% of the pressure and 80% of the volume is nitrogen? Can we do that? We can't do that. I mean, I forgot to do this. The mole fraction, well, I did this one when I talked about it. The mole fraction is equal to the pressure fraction, which is equal to the volume fraction. So a lot of people think that they think that I can just go ahead and take 80% of the pressure and it's the same thing as 80% of the volume, so it's both, 80% and 80%. And so 0.8 atmospheres and 0.8 liters of nitrogen are in there, but you can't do that because these two cannot be simultaneously true. This one is always true. The first one here is only true if what? If it's constant volume. That means the volume cannot change. And this last one here is true only if constant pressure. So if it's constant volume, the volume can't change. So that means this was false. So one of these is true, the other is false. And so you pick one to be true, the other one's got to be false. This one, we can't have both true. This is saying this one's true and this one's true. That can't happen. Right? And so you pick one or the other. And so here, if we pick pressure, then the volume has to be 1 liter. If we pick volume, that is, we say there's 0.8 liters of nitrogen, then the pressure has got to be the same, 1 atmosphere. The pressure can't change. Does that make sense? Someone?
If we rework it to make it false, instead of 0.8 atmosphere, this is 1, that would be false.
That would be false, yeah. This is why, if I'm given this, I would think, okay, this is Dalton. I would think, okay, what would Avogadro say? And then what would the mole fraction say? Mole fraction says in 1 mole of air, I would have what? In 1 mole of air, I'd have how many moles of nitrogen? If I do mole fraction, 0.8 moles. Does that answer the question? All right, what else?
Number 18, they're asking how many liters of water from the constant pressure. So we're using the ratio from the equation, so we're not always using the calculation as an estimate.
Number 18, what did you guys get for your answer? Did anybody do number 18? B? B? Sometimes well, how you know the stuff really well is, sometimes, well, actually all the time. When you start working in science, there's no solutions manual. So it's kind of nice that there's a solutions manual for this class and a complete solutions manual at that. And so that's always a luxury. But when you start working, people aren't going to ask you to solve a problem that's already been solved. They want something that hasn't been solved. And then what you want to do is, you can have confidence that you know the material well if you can spot mistakes, in here. So as an example of this, something like this problem here, number 28. After you plug everything in there and you double check and you do the calculation over and over, you realize that none of the answers are here. But you're confident that you did it correctly. And so maybe the problem was with me on this test. And so, in fact, number 28 was a problem with me. The correct answer isn't there. Did you guys get that? For 28? The correct answer is actually, would be half of this one, 4.16, or not 16, 4.18 or 4.19, like that. Times 10 to the minus 20. This one is a bit of a trick question because the mole ratio is the same as the volume ratio, which is the same as the pressure ratio. And so in a balanced chemical equation like this is the mole ratio. 1 mole of methane plus 2 moles of O2. This is going to yield 1 mole of CO plus 2 moles of water. And so the mole ratio, 1 to 2 to 1 to 2, is the same as the volume ratio. And so instead, we could do, 1 mole of gas. 1 mole of gas, do you know what 1 mole of gas occupies under standard ambient conditions? Standard ambient conditions would be room temperature and 1 atmosphere. You know how much? About 25 liters. And so this would be 25 liters. And 2 moles of gas would occupy 50 liters, 25 liters, and 50 liters. But the mole ratio is equal to the volume ratio only for gases. And so this is a bit of a trick question because H2O, if it were gas, you would be correct. It would be 50 liters. But H2O is not a gas. H2O is a liquid. And that mole ratio, which is equal to the pressure ratio, which is equal to the volume ratio, doesn't apply when it's not. And so how would we solve this particular problem? There are different ways we could solve this, But anyway, one way we could solve this is like this. We have 1 liter of methane and 2 liters of oxygen. And so this is what we call stoichiometric. This is not a limiting reagent, excess reagent, it's stoichiometric. Now, situation is this molar volume is only valid under ambient conditions. So what we're going to do is we're going to assume normal conditions. Normal conditions would be 298 Kelvin, 1 atmosphere. And so it doesn't matter which one of these I use. I'm going to just do some stoichiometry here. So I'm going to have 1 liter of methane. And then this. I'm just going to say that I'm going to have 1 liter of methane, 1 mole of gas is equivalent to 24.5 liters. I'll go with 3 sig figs. Rather than saying 25 liters, I'll say 24.5 liters. Okay. That's going to give us moles of methane. And then I'll see that there are 2 moles of water for every 1 mole of methane. And then water. So moles of water, where can I go for moles of water?
If you know the density of the grams and then the
Yeah, let's go to grams of water. So it's 18.02 grams of water per mole of water. So now I have grams of water, and then where can I go from grams of water? Yeah, because it's about 1 milliliter weighs about 1.00 grams. No, we can get it to 3 sig figs at 298. And then I'm going to go to liters. 1 liter is going to be equivalent to 1,000 milliliters. And so this one comes out to, okay, 1 divided by 24.5. This one I had memorized. But if you didn't have it memorized, you would calculate the molar volume, V over N, which is equal to RT over P. Times 2 times 18.02 divided by 1,000. .00147 1 liters of liquid water. The closest answer would be C. Although C is actually, it should be 0.0015, but it could be due to this. It's 24.46. 24.46, which is going to drop this down a little bit. So it could just be due to round off error. Or make that, will it make it bigger? No, make it smaller. Or no, it'll make it bigger. Sorry, it'll make it even worse. So we just go with the closest answer, which will be C. Yes.
So with this, you know, if we just know 25, that'd be fine, right? Because
Yeah.
just make it smaller.
Yeah. Yeah, I don't remember. If we did 25 liters per mole, yeah, make it a little smaller. That's right. And so there's some rounding error up there. And so as long as we're close within rounding error, then we're okay. All right. Was there another question?
I had a question from the chapter 5 homework.
Okay.
It was, I think it was 78B.
Okay. Splitting that up into half reactions, is that the question?
Yeah, for 78B.
78B?
Yeah.
So we have O2 minus. What's O2 minus called? Do you know? Superoxide. So we have superoxide plus water yields hydroxide and oxygen. So how did you split this one up?
Well, it says it's in a basic solution, and so I looked at the chart, and there was I think there was like, I don't know, I was struggling. I ended up doing like O2 minus plus 2 H2O plus 4E. I think that's my reduction, and then I couldn't. Yeah.
Yeah, it's this one. These are some of these are hard to split up. Some of these, yeah, you don't know which one goes to which one. Yeah. So we could try different things and see, just some trial and error. I mean, as like something like O2 minus, should it go to hydroxide or should it go to oxygen or should it go to both? What do you think? Well, it seems like water going to hydroxide seems more logical because it has a hydrogen on it, doesn't it? And so you might go O2 minus to O2 as one. And as the other, you might go, oh, let's just do water to hydroxide because oxygen and hydrogen goes to oxygen and hydrogen. And then you just try it. Well, we balance all, there's some trial and error that happens sometimes. And if it doesn't work out, you back up and see. You can correct it. But here, the oxygens are balanced, no hydrogens, just the charge. So plus an electron here. That'll take care of it. So that was pretty easy. We just oxidize superoxide. And then we go over here, and then we try to balance it. So there are no elements other than oxygen and hydrogen. We balance the oxygens are balanced, then we balance the hydrogens. When we balance the hydrogens, we have two hydrogens here, one hydrogen here, so we just add an H plus. Okay, then we balance the charge. But when we go to the balance the charge, is there any charge to balance? There's no charge to balance. In fact, if you look at this, this is not a redox. This is an acid base, hydroxide and H plus. Strong acid, strong base, right? And so we don't have any electrons here. If we don't have any electrons here, then redox is electron transfer. Somebody's got to lose. Well, superoxide's losing. Somebody's got to gain. But there's nobody gaining here. And so now we're stuck because this is not redox. This is acid base. Yeah. And so we're going to lose electrons. Who gain the electrons? So one thing we might try to do is let's say, oxidation states. So if I have superoxide, what's the average oxidation state on there? Yeah. The average oxidation state is going to be minus a half or minus 0.5. I don't have any other colors here. Grab my pen. I'll just say minus a half. What's the oxidation states here? Which goes first, hydrogen or oxygen? And oxygen minus 2. Over here, hydrogen or oxygen? hydrogen goes first, oxygen will be -2. And then over here, 0. Okay, and this, we have to watch out because there's something else that happens that can really trip you out. That's disproportionation reaction. Disproportionation reaction is where the same species is the oxidizer and the reducer. And so when I look at this, okay, either oxygen can gain or can lose in this case. If it gains, then we can go to the -2. If it loses, we can go to the 0. In this case, we have it losing. But then you might say, okay, water isn't going to go to hydroxide because if water goes to hydroxide, nobody gains, nobody loses. And so another thing that we could try with water is rather than going to hydroxide, we could just go to the same product as this. So we can have water go to oxygen. If water goes to oxygen, then we're losing here. We got -2, this is 0. And so we're going to lose electrons. But there's a huge problem because both species cannot be losers. One species has to be a loser, the other species has to be a winner. It's a zero-sum game. There's going to be a loser, and we can't all be winners and we can't all be losers. And so what do we do then in this case? That didn't work. I was thinking, oh, that would be kind of cool because if this were disproportionation in that sense, you know, oxygen being the oxidizer and reducer on the product side, then that would have worked. But you know what? I didn't try everything. You know, this is not going to work because this is going to lose. And so I'll eliminate that. Can you think of another variation of disproportionation? Yeah, we could try that. Well, not water, but to hydroxide. And so if we did superoxide goes to hydroxide, will that work? Okay, let's take a look. So we're going from -1/2 to -2. To go from -1/2 to -2, it must gain. And so superoxide is both the reducer and the oxidizer. And so that's called disproportionation too. So we can have disproportionation in the products are the same, or we can have disproportionation in the reactants. The two reactants are the same. So one superoxide loses, the other superoxide gains, or some ratio of that. We'll figure out what the ratio is depending on the electron. So let's go ahead and balance this. The oxygens are not balanced, but in this case, we're not going to balance the oxygens by adding water. In this case, we're going to balance the oxygens by multiplying hydroxide by 2. Okay, the next thing is we need to balance the hydrogens. Well, we have 2 hydrogens here. We're going to balance that by adding 2 hydrogens on the left. So we're going to have 2 H pluses. Then we'll balance out the charge. So +2 - 1. +2 - 1 is +1. 2 times -1 is -2. So we have +1 - 2. So +1 and -2, to get them to match, we need 3 electrons. As if I take +1 - 3 gives us -2, and that's equal to that. Now I have the oxidizer. And so in order to do redox, we need a reducing agent. The reducing agent loses, and we need an oxidizing agent. The oxidizing agent gains. Now the reducing agents are superoxide, and the oxidizing agent is superoxide, so it works. And so what we're going to need here, as far as the ratios goes, we'll need 3 of these. So 3 superoxides, 3 oxygens, and 3 electrons. And then the 3 electrons will cancel. And that gives us 3 superoxides as a reducer and 1 superoxide as the oxidizer. And so, I know Isabella asked me about this yesterday. Should you combine these? In one sense, yes, combine these. So we have 4 superoxides. In another sense, leave them separate. The reason I like to leave them separate is because out of the 4 superoxides, 3 act as a reducer, 1 acts as an oxidizer. So we can keep track of this as far as driving force goes. And then this is going to produce 3 oxygens plus 2 hydroxides. Now let's check if it's still balanced. So we have 6 oxygens plus 2 is 8 oxygens. And we have 6 oxygens here plus 2 is 8 oxygens. And 2 hydrogens, 2 hydrogens. And the net charge is -3 plus 2 is -1. -1 and a -1 is -2. This is -2. So this is balanced. Okay, then what I'm going to do is I'm going to identify the conjugates. So going in the reverse direction, this would be the oxidizer. So O2 is our oxidizer, number one. And going in the reverse direction, hydroxide is our conjugate producer. So this is our producer. Now we know this is skeleton, so skeleton reactions have a driving force. All skeleton reactions have a driving force. So we must be going from stronger and stronger to weaker and weaker. Here. Now there's one final step to this. Actually, I jumped ahead because this should have been the final step. The one final step is this is basic solution. In basic solution, H plus is not stable. Hydroxide is stable. So how many hydroxides do I need to add? I need to add 2 hydroxides to neutralize those 2 H pluses. So doing that on the left side, I'm going to get 3 superoxides plus 2 waters. H plus and AOH minus makes water, plus 1 superoxide is going to produce 3 oxygen gases plus, okay, now if I add 2 hydroxides to the left, I have to add 2 hydroxides to the right, otherwise everything's screwed up as far as balance goes. And so I need to add the same number of atoms and the same charge. And so this is going to be 2 hydroxide plus 2 hydroxides. Here I'm going to combine them. And so these 3 superoxides are still a reducing agent. And the water and superoxide, this is going to be our oxidizing agent. It's not as good as acid, but that's all we got. And oxygen is going to be our oxidizing agent. Hydroxide will be our reducing agent here. Again, strong, strong to weak, weak. And that would be it. So this one was a difficult one to split. Sure. And it required some playing around with it to figure it out. All right, other questions? You don't have to know the name of superoxide, but you will have to know like nomenclature. Because on the chemical reactions, what I'm going to give you the names. Like this one, I'll probably just, if I gave you a problem like this, I could probably just write up the formulas. The superoxide, I don't expect you to memorize that. But for many of the others, I'll probably just give you the name. You have to write the formula. Like I might talk about something like fluoride. Fluoride has redox properties here, has base properties here. But I wouldn't call it F minus, I'd just call it fluoride. Then you'd have to get the name. But you're going to have this chart. And so remember that you have this chart. And on this chart, I'm going to have most of the formulas anyway. So for example, I don't want to see this, which I've seen in the past. You know, I gave something, and I think I gave like sodium fluoride, and the person wrote Na2F. Na2F for sodium fluoride. How did they get that? Because sodium's on here, +1, and fluoride's on here, -1. This was in Chem 1A. Maybe in Chem 4, okay. In Chem 4, I might expect it, but in Chem 1A, you know, I gave this, and so I think, even if you did forget, okay, you forgot, but you should have been able to find it on this chart. I mean, this chart was given And so a lot of these things are given here, so be aware of that. So I don't want you to lose very many points on the first step. The first step of doing chemical reactions is to write the correct formulas. If you have the incorrect formulas, then unfortunately you've lost a lot of points right there, because that makes the rest of it wrong, unfortunately. If you can't, and this is something I've said, I forgot to say it in the morning, but if you can't remember something and it's preventing you from solving, the problem, then you can ask me. I'll deduct points for the nomenclature, but not for the entire reaction. But hopefully you can get all the formulas for that.
Do we have a nomenclature section, or are you just talking about building the formula for the question? Or do you have another section specifically for nomenclature?
No,
Okay.
it'd be like this.
Oh.
No, that's not like that. More like that. It would be like the practice handout I gave, the worksheet. I didn't have very many reactions on this. Here. You're going to have chemical reactions. Like I mentioned before, that's one of the differences between old exam 1 and old exam 2. Or very, very little predicting chemical reactions, because I did the sequence differently in 2017. And so just be aware that you're going to have more chemical reactions on your test than what was shown. And so I gave you that handout. And so you can expect like a metathesis, acid base, redox, chart, method, a skeleton, maybe a combustion or something, or other. Depends on how much room I have. We'll see. All right. Well, anyway, we're out of time. So if there are more questions, it's my office hour time. So I'll stick around if you have questions. Well, good luck tomorrow.